Hello, everybody. This is Sunday. It's October 30th, and we are heading into Module 10 of our online astronomy course. Now, tomorrow is Halloween. That might be when you are viewing this, so I wish you all a very happy Halloween. But if you're viewing it some other day, then I'll just say greetings, and let's start talking about what's in Module 10. Now, as you can see from the background behind me, we're finally studying the stars. Now, last week's module, we studied the nearest star, our sun, but the next two modules will be talking about other sorts of stars. What are these stars like? How are they born? How do they live their lives? And how do they die? We'll be finding out all of that. But in this module, Module 10, we're going to find out how astronomers know what they know about the stars. And you're going to be learning the basic techniques that all astronomers use for studying the stars. There are others, of course, and there are spacecraft out in space making measurements, but even those spacecraft are going to use the techniques that we're going to be talking about today and learning about this week. So, what is the most basic thing you might want to know about a star? Well, looking at all these stars, I'll tell you right now that all of the stars here appear as little points. There are other objects that maybe appear like, they're reddish blurs or something like that, and those are other galaxies. We're just talking about the stars, the bright points of light, like this one here. Oops, yeah, that one there, or this one here next to my shoulder. Those are stars. And the most basic thing you might want to know is, how far away are they? And the answer is, qualitatively, they're very far away. Some of them are extremely far away. Some of them are rather close, though. And those that are close, we can measure the distances to them using a surveyor's technique called parallax. Now, if a surveyor is trying to measure the distance to a mountain, the surveyor might put his instrument on the ground and take a sighting toward that mountain from one position, then move a number of yards, say 100 yards away, and then take the sighting on that mountain from another position. And that angle, the difference in the directions he has to look, will tell him the distance to the mountain. Well, we're going to do the same thing with the stars. Astronomers do the same thing with the stars. And so we want to make the distance between one observation and another observation as large as possible. So how big could that possibly be? And the answer is that you can look at a star when the Earth is on one side of its orbit around the sun, and then you can look at that same star when the Earth is on the other side of its orbit 6 months later. And that's what astronomers do. They use a very long baseline. The baseline is the distance between those two observations, and use a long baseline to take a look at nearby stars. Now, the distant background stars are so far away that they're not going to appear to move. They're just very, very far away. But a nearby star will appear to move against the distant background stars. And of course, that star is not really moving. What you're doing is you're seeing it from different points of view. And so let me illustrate that, and we'll do something here together. And you can all do that. I want you to get yourself so you're about an arm's length away from the screen that you're looking at. And I want you to pick one of the stars here on the screen. Maybe it's one of these bright stars. Maybe this one on the edge of the screen, or this one that's close to my shoulder. Any of these bright stars, just pick it. And that's going to be a distant background star. That's a distant background star. Now, we're going to pretend that your nose is the sun, and one eye is the Earth when it's on one side of the sun in its orbit, and the other eye is the Earth when it is on the other side of its orbit 6 months later. And we're going to hold out our thumb. Right about, you can have your elbow against your chest and just hold out your thumb, just like that. And you can line your thumb up with one of those stars and close one eye. So close one eye and line up that thumb over one of the stars, and you'll see it's exactly covering that star. And that's like looking at that star from one side of Earth's orbit around the sun. Now, don't move anything, but just switch eyes, like you're on Earth 6 months later, and you'll find that your thumb is no longer covering that star. Now, your thumb didn't move, that distant background star didn't move, but your thumb, which is a nearby star, appeared to move because you were looking at it with one eye, and then from the other eye in a slightly different position. Same thing for parallax. We're looking at a nearby star as it seems to shift position because you're viewing it from one side of Earth's orbit and then the other side 6 months later. Now, even for the nearest stars, that is a very, very, very small angle. And in fact, we don't measure that angle in degrees. We measure it in arc seconds. Now, you might remember that 1 degree is divided into 60 parts, and those are 60 minutes in 1 degree, 60 arc minutes in 1 degree. And we divide each one of those minutes into 60 parts. And each one of those parts is an arc second. It's 1/3600th of a degree. And that's pretty small. So it's not surprising that it took a long time for the first parallax to a star to be measured. And in fact, I have a book here, an old book, and I'll show you what it is. This is an introduction to astronomy. It's an old astronomy book, but you can see it's an introduction to astronomy. It's for students of Yale College, and it is published in 1839. So here are all the pages of that book that you can see, and all this much of the book right here, the great vast part of the book, is about the solar system. And only this much of the book right here is about stars and galaxies in the universe. In fact, they didn't even know there were other galaxies at this time. So it's just this much. So part 3 here of the book, starting on page 243, is about the fixed stars in the system of the world. And it's not until later on page 266 that they're talking about the distance to the stars. And so let me read you. It's here in a footnote because the book was going to be published, but then the author found something, heard about something, and had to include it, so he included it in a footnote. And here I'm going to read the footnote for you. It says, very recent intelligence informs us that Professor Bessel of Königsberg has obtained decisive evidence of an annual parallax of the star 61 Cygni amounting to 0.3136 arc second, so about a third of an arc second. This makes the distance of that star equal to 657,700 times the distance to the sun. And that is a distance it would take light 10.3 light years to traverse. And that's a pretty good value to the stars. 61 Cygni, it's about 11 light years. But we are going to use units, not of light years, but of parsecs. Now, a parsec is 3.26 light years. So, why do astronomers use this? Why do they just grab this number out of the air? Well, 1 parsec is the angle that the radius of Earth's orbit around the sun would make, that one astronomical unit would make, when that is 1 arc second. When that angle is 1 arc second is viewed from Earth over here. I'm sorry. So here's a star, and looking at that star from 2 points 1 AU apart, that angle is 1 arc second. So parallax means parsec means parallax arc second. Parsec, parallax arc second. It's the distance you have to be away from Earth's orbit so that one astronomical unit, the distance from Earth to the sun, has an angle of just 1 arc second. A parsec is 3.26 light years. You'll get used to it because we need a big ruler to measure large distances. Now, for distances to stars, we're going to use parsecs. Now, what else can we know about light? Well, we now know the distances to a lot of stars. Thanks to the Gaia spacecraft, it has been measuring the distance to 1 billion stars within our Milky Way. And its parallaxes are accurate to several millionths of an arc second. So we can tell the distances to some very distant stars, and we can really map out the Milky Way using parallax now. For other galaxies, we need other methods, and you'll be finding out about those in the next module. Now, you also know that if I have a flashlight and I shine it on the wall, I get a little circle of light on the wall. Now, if I go twice as far from the wall, that circle gets twice as wide. Now, if the circle is twice as wide, that means it has 4 times the area. That means that light is spread over 4 times as much area as it was when I was closer. And so when I've doubled my distance, the light is concentrated only 1/4 as much. In other words, if I had a star, I was looking at how bright that star was, and then the star was moved twice as far away, it would only appear 1/4 as bright. If it were 3 times as far away, it would only appear 1/9 as bright. And this is called the inverse square law for light. And it's one of the basic tools that astronomers use. Now, there's a lot more we can find out about stars. And stars, like our sun, are big balls of gas. They have a certain surface temperature. They have a certain radius, certain size. And they have a certain luminosity. And luminosity is just the energy per second that the star gives off. The energy per second in light that the star gives off at all wavelengths. And that's measured in watts. Just like a 100-watt light bulb gives off a certain amount of light, a star gives off a certain amount of light. And remember, the sun is equivalent to 400 million. Well, that's its luminosity in watts. 400 million watts. So stars are quite bright. And you might wonder, well, what determines how bright a star is? Well, hotter stars give off more light. From each square meter of its surface, a hotter star will give off more light than a cooler star. So a bluer star, bluer stars, remember, are hotter, will give off more light per square centimeter than a red star will. Now, the other thing that determines the star's luminosity, is how many square meters it has, its surface area. And the surface area depends upon the square of its radius. You might remember, or you might not, either way, the surface area of a sphere is 4 pi r squared. And so the luminosity depends upon the radius of the star squared. And it turns out it depends upon the temperature of the star to the 4th power, because that is a characteristic of black body radiation, which is what the light is. Stars are big, hot, dense balls of gas, and they give off black body radiation. And you'll learn about that relationship in this module. And let me emphasize here for the first time, please read the module introduction, because I go through in a lot more detail some of these laws that we're going to be using and that astronomers use. Also, astronomers talk about the brightness of a star in another way. And this goes back a long way, back to an astronomer in ancient Greece named Hipparchus. And he made the first star catalog. And in fact, just this week, a little bit of cool astronomy news. Astronomer Hipparchus's catalogs were believed to be lost, but a page of that catalog has been discovered. And so for the first time, we can actually see words that Hipparchus wrote when he made the first catalog of some 800 stars. Now, Hipparchus called the brightest stars first magnitude. That is a star of the first magnitude. In other words, that is one of the brightest appearing stars in the sky, or stars of first magnitude. Slightly dimmer stars are second magnitude stars, and slightly dimmer than that, third magnitude, all the way down to 6th magnitude. And 6th magnitude is the dimmest star you can see with the naked eye, which is all Hipparchus had. And we still use the magnitude system today. Astronomers use the magnitude system, and in fact, it has been carefully adjusted so that the magnitude system today is in good agreement with what the magnitudes that Hipparchus assigned to different stars. So, and notice that smaller numbers mean a brighter magnitude. So a first magnitude star is brighter than a 6th magnitude star. And in fact, if I subtract 6 minus 1, I get 5. And 5 orders of magnitude means a factor of 100 in the energy I am actually receiving from that star. So we are receiving, is what I want to say, we are receiving 100 times more energy from a first magnitude star than from a 6th magnitude star. Now, these are called apparent magnitudes because they are how bright a star appears to be in the sky. But we don't know whether a star appears bright because it's really bright and far away from us, but maybe it's just dim and really close to us. We don't know. You know, to really compare the magnitudes of 2 stars, we would have to get some sort of cosmic tow truck and tug and move them all out to the same distance. And we can't do that physically, but astronomers can do that mathematically. And so they move all of the stars out to 10 parsecs. And they ask, how bright would that star be if it were 10 parsecs away? And they assign that star an absolute magnitude. An absolute magnitude of a star is how bright the star would be if it were 10 parsecs away. And so a star's absolute magnitude doesn't depend upon its distance, whereas a star's apparent magnitude does. The further away a star is, according to the inverse square law, the dimmer that star is going to be if I just move that same star. Well, now, you might imagine that from just what I've been saying, that the distance to a star, its absolute magnitude, and its apparent magnitude are all tied up together. And there is an extremely useful formula It's not in your book, but it is in the course introduction, and you are responsible for it. So please look at the course, the module introduction in your on Canvas. And that is an equation that links the apparent magnitude, the absolute magnitude, and the distance of the star in parsecs. So that if I know the apparent magnitude and the absolute magnitude, I can find out the star's distance. This is fantastic, except it sounds like, well, gosh, I have to know the absolute, to find the absolute magnitude, I have to know the star's distance in the first place. So thanks a lot. That gets me nothing. But no, there's a way of finding the star's absolute magnitude without knowing its distance. You'll find out about that next week. What else can we find out about stars? Well, you already learned in module, let's see, I guess it was module 3 or 4, I forget which, about the dark absorption lines that are in a star's spectrum. And early in the previous century at Harvard Observatory, there was a group of remarkable women, and they were assigned the task of looking at these spectra, because at that time they had film that could take pictures of stars. They would put a prism in front of the film, and the star images would be stretched out into a spectrum so you could see the dark absorption lines in the star's spectrum. And the women were given a task of bringing some order to this. And they noticed that certain lines would fade into other lines, would fade into other lines. And so they did what seemed reasonable at the time. They assigned them letters of the alphabet. These stars look like, we'll call these stars A, B, C, D, E, F, G, and so on. Now, it fell to a woman named Annie Jump Cannon to realize that no, that this wasn't the right sequence. And if you put the stars in the sequence O, B, A, F, G, K, M, that is a sequence from the hottest stars to the coolest stars. O stars are the hottest stars. They're big and they're blue. M stars are cool stars. They're red. And so this is called the spectral sequence, O, B, A, F, G, K, M. And generations of astronomers have learned this by a simple mnemonic, a simple phrase to help them know the order. And here it is. O, B, A, fine, girl / guy, whichever you prefer, kiss me. So O, B, A, F, G, K, M, O, B, A, fine, girl / guy, kiss me. And by studying these spectral lines, you've already learned we can tell what the stars are made of in an earlier module. Well, we can learn the star's temperature and its temperature sequence, and you can make very precise measurements of stars' temperatures with these spectral lines. Now, also, suppose the star is moving. Now, you might remember there's something called the Doppler effect. And how can we find out how fast stars are moving? Well, a man named Christian Doppler put some trumpets on a railroad car and had that railroad car go past him several hundred years ago, playing a note that he knew. And he found out that as the car was approaching him, the pitch would be higher. And as the car was moving away, the pitch would be lower. And that's called the Doppler effect. And that affects light, too. And so if a star is moving toward us, it's catching up with its own light waves. It's catching up with its own light waves. And that means the light waves are becoming shorter. Remember, shorter wavelength light is bluer. And so if a star is moving toward us, its light becomes bluer. Now, it's a small shift that doesn't change the color of the star, but the absorption lines in the star's spectrum can shift. And so we can tell the speeds of the stars. If a star is moving away from it, it's running away from its own light waves, and that stretches out the light waves. and the wavelength becomes longer. That's redder light. It's a redshift. And so the light from a star moving away from us is redshifted, and we see that in a motion of the spectral lines toward longer wavelengths. So there's a lot we can learn from just looking at light and those absorption lines. Finally, how can we know the masses of stars? Well, it turns out about half the stars in the sky, at least half the stars in the sky, are binary stars. There are two stars that orbit around each other, held together by their own gravity. And you might ask, which star orbits which? And the answer is neither of them. Both stars are moving, and they're moving around their center of mass between them. You know, if I were to put the two stars on a scale and like a teeter-totter, then where that teeter-totter would be balanced, that's where the star's center of mass is. And they both move around that center of mass. And how they move, the time it takes to go around once, Kepler's laws, plus understanding how far away the star is, so we know how wide the orbit is, those can tell us the masses of the stars. So that's just really amazing. We have a wealth of information that can tell us about those stars. Now, one more thing, and that is astronomers have to organize that information. And they organize that information using something called an Hertzsprung-Russell diagram. This was first made by Einar Hertzsprung and Henry Norris Russell about 100 years ago. And I'll move to the side here so you can see what it is just a little bit better. On the bottom axis, on the horizontal axis, you can see the star's spectral sequence, O, B, A, F, G, K, M. So hot stars on the left, cool stars on the right. So these stars, you can see at the bottom there, have a temperature of about 30,000 degrees on their surface. Excuse me. And these stars have a temperature of about 3,000 degrees, the M stars, 3,000 degrees on their surface. On the vertical axis, on the other hand, running up and down this right-hand side here, is the brightness of the star compared to the sun. So 1 means the same brightness that the star has. 10 means 10 times the sun. I'm sorry, the same brightness that the sun has. 10 means 10 times the sun's brightness. 100 means 100 times the sun's brightness. 1,000 times, 10,000 times, 100,000 times, 1,000,000 times the sun's brightness. And down below, we have 1/10 the brightness of the sun, 1/100th the brightness of the sun, 1,000th the brightness, the luminosity of the sun. So this is the luminosity in solar units. And amazingly enough, between 80 and 90% of all stars fall on a band. And that band runs from the upper left-hand corner down to the lower right. Need some drink here. And that's called the main sequence of the HR diagram. 80 to 90% of all stars lie on that band from the upper left that go down to the lower right. What do all those stars have in common? Why does that happen? We'll find out about that in a later module. Now, there are stars in other places in this diagram too, because up here, there are giant stars, stars many times larger than the sun. And up here, supergiant stars. And finally, down here are small stars called white dwarfs. So what are these stars? How did they get to be white dwarfs. We'll find out that all stars, when they are born out of a cloud of gas and dust, are born on this main sequence here. And as the stars age, they change their characteristics. And so they move not on space, but their position in the HR diagram changes. That moves them into the giant or supergiant part of the diagram, and then down to the white dwarf part. And we'll be talking about that. We talk about the evolution and the death of stars. Whew. There's a lot in this module, and I've been talking for a long time, and my voice is getting a bit hoarse. But before I go, I do want to pull up Stellarium here. So let me do that. I will pull up Stellarium. Let's see here, because there's something cool going on. There's Stellarium. And I think you can see that we are on, this is on the 1st of November. So this is Tuesday, the 1st of November. That is the day of the first quarter moon. And on the day of the first quarter moon, it's going to be right below Saturn. Here I am out at about 8 o'clock looking south. There's the moon right below Saturn. And over the next several nights, it will move across sky. So Thursday, it's going to be very close to Jupiter. And seeing that quarter moon next to Jupiter, Jupiter's really bright in the sky right now. And that's really going to be cool. So let's go back here. In fact, I'll even go back to Halloween. Here's how the sky will look on Halloween. And you might wonder, well, what constellations are these in? And so let me put up constellations. Right now, or on Halloween, the moon will be in Capricorn. And Capricorn, you might remember, is that half fish, half goat. I don't know what the Greeks were thinking of when they named these things, but there they are, half fish, half goat. And then over the next couple nights, the moon will move through Capricorn. And there is, that's on Wednesday, it's entered Aquarius. And finally, on Thursday, it moves into Pisces. So let's just go back here. Here is Monday, Tuesday in Capricorn, Wednesday, Thursday in Aquarius, Friday in Pisces. And I might be wondering, well, how do I know what constellation that they're actually in? Well, I can put up the constellation boundaries. The sky is divided up into 88 constellations. And who decides on what these boundaries are? The International Astronomical Union creates the official boundaries. So you can see that Monday and Tuesday, Halloween, and the next day, it's in Capricornus. Next 2 days, Aquarius, finally entering Pisces on Thursday. So take a look, especially on Thursday, it'll be really cool. Okay. Well, that is it. A lot to know, but this is the key. This module gives you the keys to understanding the universe and understanding how astronomers know about the universe. And I really hope you enjoy learning about it. So happy Halloween, and I will look forward to seeing you next time. So until then, bye-bye.